example number 2 is the last thing that we did on Monday, where we were checking for independence. So we could figure the probabilities out that we were going to need. I guess we didn't really have to do much to get the probability of B2 given G1. We already had it. But we did have to go get the probability of B2, which we could do based on other stuff that we'd already computed. And once we had those, we just had to check and see if the numbers were equal. And since they're not equal, then the events B2 and G1. So first student being chosen being a girl and second student being chosen being a boy, those are not going to be independent. Number 3, down here underneath, is the other way around. So number 3 is you know the events are independent, and that can actually be used in order to figure out the probability of an intersection. So the key thing with number 3 is right here, that the fire engine and the ambulance operate independently. So we know that. So because they're independent, we know the probability of the intersection will be equal to the product of the individual probabilities. And then we've got a couple of given probabilities here. So I guess if I say maybe F for fire engine and A for ambulance, then the probability of F, the fire engine being available, is 0.98. And then the probability that the ambulance is available is 0.93. So we do need those. And then we want the probability that both are available. So both would be an intersection. And that is what we're going to be able to get knowing that the events are independent. So that really comes in handy here. So the probability that both are available is going to be the probability of F and A, or the probability of F intersect A. But because the events are independent, we can do this and say this is equal to the probability of F times the probability of A. So that maneuver right there you cannot do all the time, but you can if the events are independent. So right there, this is due to the events being independent. Right, so that's one of those things where it would be nice if you could do it all the time, but you can't, only in a situation like this where you know the events are independent already. And since we already have these numbers, go ahead and substitute in. That's a 0.98. And then probability of A for ambulance is 0.93. And what we end up with is 0.9114 if you multiply those out. So number 3 is the same concept as number 2. It's just the other way around. It's now we know that the events are independent, and so then that tells us, oh, well, we have a different way of getting the intersection that we don't usually have. We're getting the probability of the intersection. Number 4 is similar to number 3 in the sense that we've got independent events again, and we can use that, but we just have more of them this time. So now instead of 2 events, we have 3 events. It's still going to work the same way, though. So what we've got is that a manufacturer of a flu vaccine concerned about the quality of the flu serum, and batches are processed by 3 different departments, and we've got the rejection rates there. Right? So first department has a rejection rate of 0.1, second 0.08, third 0.12. And the inspections by the 3 departments are sequential, just meaning it goes first, then second, then third. And they're independent of each other. That's the part that's important for this section, obviously, right? We just had it in the last example. So the first part of this is what's the probability that a batch of serum survives the first inspection but is rejected by the second. Okay, so what we've got then, I guess we can write it maybe like this. The probability of pass first and fail second. But we do know that these are independent events, so because of the independence, we can do this and say this will be the probability of pass first multiplied by the probability of fail second. And we don't have the pass probability, but it's not that hard to figure out because if we have the failure ones, I mean, it would have to be the complement for passing, right? There isn't a third option there. So if the rejection rate, so the failure rate for the first inspection, that's 0.1, then the pass rate has to be 0.9 because it's one or the other of those things that has to be taking place. So 0.9, and then the chance that it would fail on the second inspection is the 0.08. And so we would just have to multiply those out, and you get 0.072. Right? If 9 times 8 is 72, 0.9 times 0.08 must be that. Then part B, rejected by the third department. So it has to get there first, right? Because if it's rejected by the first department, it's just rejected right there. It doesn't keep going. So in order for it to be rejected by the third department, it would have to pass the first and pass the second, and then get to the third and be rejected there. So this has 3 events. It still works the same way. It's just going to take a little bit longer to write out. So this would be the probability of pass first and pass second and fail third. So pass first and pass second and fail third. And even though there are 3 events, this still works the same way. We know they're all independent. So we can write this as a product of 3 things this time, right? Since there are 3 components here. So we have the probability of pass first times the probability of pass second times the probability of fail third. And let's see, we know pass first is 0.9. We already have that one. Pass second would be 0.92 because for the second one, the failure rate or the rejection rate is 0.08. So 1 minus that is 0.92. So we get that here. And then fail third is the 0.12. And if you multiply this out, you get 0.09936. I think I can squeeze this all onto one screen here. There we go. So very slightly less than 10%, I guess, is what we're ending up with here. That it would make its way to the third department, but it would fail once it got there. The last thing in this section is the difference between mutually exclusive and independent events. Because this is one of those things where if you're not used to these terms, if you haven't seen them a whole bunch, it is easy to sort of conflate these things. So the difference between them, so independent events, which is what this section mostly is about, that's where you have 2 events that have no effect on each other, right? They have no effect on each other's probabilities, right? If one happens or it doesn't happen, that has no effect on if the other one happens or doesn't happen. Mutually exclusive events are just ones that can't happen at the same time. Those also can't be independent. Right? Because if they can't happen at the same time, then you go, well, if one happens, the other one couldn't. So that's definitely affecting the probability. So that's this part in green. So mutually exclusive events, empty intersection. So if A and B are mutually exclusive, like if you kind of did some of these things that we've been talking about with the independence check, like you get the probability of the intersection, or if you get one of the conditional probabilities, they're going to 0, right? Like if they can't happen at the same time, they got to have an empty intersection, right? They can't occur simultaneously. Empty intersection, the probability of intersection is 0. But then that's the numerator for the conditional probabilities, so they're also going to be 0. So you can't have events that are both mutually exclusive and independent. There's just no way to get that to work. And you could see it algebraically, right? Because whatever events A and B are, presumably their probabilities are not 0. So, you know, whatever the probability of A is, it's not going to be equal to the probability of A given B if the probability of A given B is 0. Right? And you can make the same kind of argument down here with the probability of B given A compared to the probability of B. So if you want to look at it algebraically, like that will hold up, that there's no way you can have events that are both mutually exclusive and independent at the same time. And so just make sure you're comfortable with these terms because, like I said, if you're not used to them, it is easy to kind of confuse the two. Section 4.8, judging by its title, is about counting things. This does get a little more complicated as we go through it. The first page isn't too bad. I think that's one where you can just kind of reason your way through it and you'll get the right thing. But we do kind of bring in some factorials, so if you're not used to those, they are coming. There are ways where you can simplify factorial expressions relatively quick, and that'll come up too. So the basic counting rule, which is what the first page is about, is just that if you have two different events where one has a certain number of options and the other one has some possibly different number of options, then to figure out the total number of possible outcomes, you can just multiply. And that's pretty much what this is getting at. So like here, if set A consists of m elements, set B consists of n elements, then the number of ways you can pick one thing from A and one thing from B is m times n. This is also the way that you kind of think about, like if you're rolling two dice, how you get, like, well, there are 36 possible outcomes. You get 6 outcomes on the first die, 6 outcomes on the second die. 6 times 6 is the 36. So it's that idea, just maybe with some different contexts here. And you can have more sets, too. You don't have to just have 2 of them. But the first one just has 2 of them with the ice cream cones, because you have a few different options for the type of ice cream. So that's set number 1. And you have 2 options for the type of cone. That's set number 2. So what we end up with here is we have 4 possible choices for ice cream, and then we have 2 for the cone, and so we end up with 8. So let me just label these. So 4, that's the ice cream, and then 2, that's the cone. So 4 options for the ice cream times 2 options for the cone, 8 total. You could write them all out if you wanted, right? Vanilla with sugar cone, vanilla with waffle cone, chocolate with sugar cone, chocolate with waffle cone. So you could do it that way, I guess, using the method of exhaustion here, because there really aren't that many, right? There are only 8 total. But these numbers get bigger pretty quickly, so I don't think the method of exhaustion is going to be very efficient for some of these other ones. Even in number 2, because in number 2, we have 3 sets this time, right? 8 sandwiches, there's set number 1. 4 sides is set number 2. 5 drinks is set number 3. So this is going to be a much larger number that we're going to get in number 2. I scroll down a little bit here. All right, so then what we're going to have is 8 for the sandwiches, times 4 for the sides, times 5 for the drinks, and that is 8 times 20, so that must be 160. So yeah, I wouldn't want to do that one by exhaustion. That's a long list, 160 things. And then that one is nothing compared to what happens in number 3. So number 3 is kind of taking this to a conceptual extreme. And I know that if you're going to order a custom laptop, there are more options than this, but I had to cut it off somewhere so this didn't get too long. So 7 options for the processor, 5 for the screen size, 6 for the capacity of the hard drive, 4 for the memory, 4 for screen resolution, 2 for color. Okay. How many combinations are possible? Well, you multiply all those numbers of options together, right? Because it's like we have a set of possible processors where you have to pick one. You have a set of possible screen sizes where you have to pick one, right? So it's going to be 7 times 5 times 6 times 4 and so forth. So it looks like we'd have 7 times 5 times 6 times 4 for the memory, and then another 4 for the screen resolution, and then 2 for color. If you multiply this all the way out, it's 6,720. And that's what you get for the number of possible combinations of specifications there. And now, the factorials. So, n factorial, where n is some positive integer, it's written with an exclamation point. So 15 exclamation points would be 15 factorial. That kind of thing. And it's the product of the integers from 1 to n. They're usually written the other way. They're usually written in decreasing order. So like like how the 7 factorial right here, it's 7 times 6 times 5 times 4 times 3 times 2 times 1. I think that's the more conventional way of doing it. So 1 factorial, like, okay, well then that's just a 1. 2 factorial, 2 times 1. 3 times 2 times 1. 4 is 4 times 3 times 2 times 1. Right, so the bigger you go, then the longer the string of numbers you're going to have that are multiplied together. Also, it's not listed here, but it will show up later. 0 factorial by definition is 1, not 0. We will need that eventually. All right, so simplifying some expressions with factorials. This 5 factorial, that one we just want to expand it out. So this would be 5 times 4 times 3 times 2 times 1. And if you multiply that out, that's 20 times 6, so that's 120. But the more interesting thing, and the thing that we're actually going to need when we get into Chapter 5, is what you do when you have quotients that involve factorials. So like this. There is a strategy here, and that strategy is try to cancel as much as you possibly can. So if I expand these out, so 8 factorial be 8 times 7, 6, 5, 4, 3, 2, and 1. Then on the bottom, 6 factorial would be 6, 5, 4, 3, 2, and 1. And then look at how much we get to cancel. Because 6 is a factor of the top and the bottom. So is 5, so is 4, so is 3, so is 2. I guess you can cancel the 1s even though that doesn't really have an effect. But look at what we're left with. Really, now we just have a 1 on the bottom. So this is just 8 times 7 over 1. So that's just 56. So canceling things, rather than multiplying everything out and then dividing, canceling is definitely the move, because that keeps the numbers nice and small. And then number 6, this is the kind of thing that you have to do a lot of later in this section and also in Chapter 5, where it's this quotient, and if you look at the factorials on the bottom, like how the 5 and the 4 add up to 9, that's not an accident. But with this kind of thing, there is a strategy for getting it done faster. So what will always happen with these, like this one in number 6, that will be an integer at the end. Like once we have everything simplified. But first, I'm going to expand everything out, and then we'll see what we can do. So 9, 8, 7, 6, 5, 4, 3, 2, 1. And then on the bottom, we have a 5 factorial. And then we have a 4 factorial. So we can expand them all out. And then the best thing to do is that you can always cancel one of the factorials on the bottom all in one shot and then kind of do the other one piecemeal. So when you're going to do the one all in one shot, make it the bigger one. So here I know it's not that big of a difference. You have 5 factorial versus 4 factorial. Yeah, I mean, I would still do it with the 5. That's a little bit bigger. But if it was, you know, instead of 5 and 4 on the bottom, if it was like a 7 factorial and 2 factorial, you'll save a lot of time if you get rid of that 7 factorial first. So what I'm going to do here is I'm going to cancel all this right here with this right here, right? So 5 factorial is gone. And then do whatever else you can do. You should be able to cancel everything on the bottom. So 4 times 2 is 8. So I could just say 4 and 2 with this 8, and that's all gone. And then the 3 goes into 6, or the 3 goes into 9. You can play that one either way. I'm going to go 3 into 9. So then all I'm left with is 3 times 7 times 6. And then I've got a 1 on the bottom, right? So, all right, that's really just 3 times 7 times 6 then. And that's 21 times 6, so that is 126. And there we are. So that strategy of get rid of the big factorial, we are not done with that. That will show up again later when we get into the combination part of this. The next two things are called permutations and combinations. The difference between those is with permutations, order matters, and in combinations it doesn't. So, like it says here, since it's an ordering, the position of individual objects matters. So, like, if one is in the first position or the second or the third, that's something different than if it's the same integers or the same values but kind of rearranged. So, that's like this thing here with the 6-digit numbers. There are 3 6-digit numbers that you can make out of the digits 7, 2, and 9, and those are all distinct numbers, right? 279 is not the same number as 792, even though they have the same 3 digits. So the way that you can figure out how many possible permutations there are is just to kind of go, okay, how many are in the first position? And then if one of them's used, how many are left to go in the second position? Now 2 of them have been used, how many are left to go in the third? And to do it like that. So the way that I would do this is just to say, okay, for the 7, the 2, and the 9, then you have 3 options for the first digit, because it could be 7, 2, or 9, but then one of them gets used. So when you get to the second digit, you only have 2 possibilities, right? Like if the 9 went first, then when you get to the second digit, you only have 7 or 2, or you only have 2 choices. And then when you get to the third digit, 2 of them have been used, so you just have 1 left. So let me just kind of label these here. So that's for the first digit. The 2 is for the second. And then if 2 have already been used, then you only have 1 left for the third digit. So what we're ending up with, it looks like, is 6, right? 3 times 2 times 1. So that is what you get here. And then what if you could repeat digits? Well, if you could repeat digits, then that's not actually a permutation, but I mean, this argument is worth making, I think. Then you just have 3 options every time, right? Because then you could use 7, 2, or 9 in the first digit, but then whatever you used would be in play again, right? Because you could have things like 7, 7, 7, or 9, 9, 2, right? So you can have repeats. And so then you say, okay, well then it's just 3 every time, right? So 3 there, then 3 in the second digit, and then 3 in the third. So that's 3 to the third, which is 27. So there are actually a lot more options if repeats are allowed. In permutations, typically they're not, because the individuals are considered to be distinct, so you couldn't have multiple copies of them. Like if they were people, or like in number 7, if they're horses, right? There's only 1 copy of one particular horse in existence, right? There is not a clone, so we can't have repeats. So that's what number 7 is about, right? That one is about horses. So 20 horses in the Kentucky Derby, and how many different possibilities are there for the horses to finish first, second, and third? Well, then there would be 20 options for finishing first if there are 20 horses to begin with. But then one of them has to finish first, so then there are only 19 options for finishing second. But then if one finishes first and another one finishes second, there are only 18 options left for finishing third. So we got first, second, and third. And if you multiply this out, this is a kind of decent sized number here. You end up with 6,840. At the top of this next page, there is a formula to compute the number of permutations. I never use this, to be perfectly honest. I think this, to me, this feels like taking the long way around. You can do it, it will work, but it's more effort than just kind of reasoning through it. And I'll run through it with the donuts down there, but you'll see. It's easier just to kind of reason your way through it. So in the formula, the P clearly stands for permutation, right? So NPR means you're starting off with N things, and it's like how many different ways could we order R of these N things, where R can't be bigger than N, right? It's like with the horses, that would be 20P3, right? Because 3 for first, second, and third, right? It's that group of 3 for finishing in the top 3 places out of the larger group of 20. And you can do this, and it'll work. You'd end up with 20 factorial over, I guess, 17 factorial, and you could take it from there. So, yeah, if you divide 20 factorial by 17 factorial, you can cancel the 17 factorial on the top and the bottom, and you'll end up with 20 times 19 times 18, which is what we had. And then I'll run through it here with the donuts. And I realize those are overly perfect donuts, but I think I took this maybe out of a topology book, which has a lot of donuts. In topology, they're called a torus, but it's the donut shape. And I probably just colored them so they look like they were, deep fried. They were deep fried dough. Let's see. So here we have 14 donuts, and we have to put 5 of them in the case. And we're saying it matters where they are, right? It matters which one's on the left, which one's on the right, which one's dead center, right? That kind of thing. So then R is 5, right? Because we're picking 5 out of the 14 donuts. So if you use that formula up there, that would be 14p5. And so then that's 14 factorial over 9 factorial, right? Because 14 minus 5 is 9. And then if you expand these out, you'd have 14, 13, 12, 11, 10, and then I'm just going to write this as a 9 factorial. You could write it all the way out, but I know I'm going to cancel that with the 9 factorial on the bottom. So I think we can kind of stop there and just say, okay, this is the plan. We're going to cancel that 9 factorial on the right side of the numerator with the 9 factorial in the denominator, and then we do that. Then what you will end up with is 14 times 13 times 12 times 11 times 10, which is 240,240. So we've got quite a big number this time. But I think here you can see where you could view this as taking the long way around. Because if you just kind of reason your way through it, you'd be like, all right, up here, donut number 1, there are 14 options, but then one of them gets used, right? You got to use a different type every time. So there are 13 options for donut number 2. But then there are 12 options for donut number 3, and then 11, and then 10. So if you just kind of reason your way through it, you end up down here right away. And you don't have to use this formula. So you can use the formula if you want to, but I'll admit, to me, it does feel like it's taking the long way. Now, combinations. So the difference between permutations and combinations is that with combinations, the order does not matter. So that's just, we are going to select a group of individuals from a larger group. We're just going to pick 5 individuals out of 23 or something like that, right? And the order doesn't make a difference. We just need a group of 5. So this is a little bit different computationally. You do want the formula here. To try to reason through it is a lot harder. This one, I think it's definitely helpful to have that formula. So here's the combination formula, and this is very similar to, if you go a couple of pages back where there was the 9 factorial over 5 factorial times 4 factorial. It's that, just generalized, but it's that idea. Because watch what happens in this first example. If I expand this out, then what I'm going to end up with is 8 factorial on top, right? Because that's the n, and right, out of n distinct objects, how many ways can you pick 5, right? That's what this is really asking. So we'd have a 5 factorial, and then an n minus 5, which is 3 factorial. And then if you expand everything out, so on top we'd have 8, 7, 6, 5, 4, 3, 2, and 1. And then on the bottom, we're going to have a 5 factorial. And then we're going to have a 3 factorial. And just like before, I think the correct strategy is get rid of the bigger factorial on the bottom first before you do anything else. We're just simplifying these. So 5 is bigger than 3, so get rid of that 5 factorial. So I'm going to cancel this right here with this up here. And then anything else that you can do. So 3 times 2 is 6, so I can do that. And I'm just left with 8 times 7. with a 1 on the bottom, right? Like, when you're left with a 1 on the bottom, there's nothing else you can cancel. So, 8 times 7, 56. Got it. Next, how many ways can we pick 4 things out of 12? All right. Well, then, we know this is going to be 12 factorial over 4 factorial times 8 factorial. So the strategy is going to be get rid of the 8 factorial, since 8 is definitely bigger than 4. So I'm just going to write out the top until I get down to the 8 factorial instead of expanding the 12 factorial all the way out. So I'm going to have 12, 11, 10, 9, and then 8 factorial, like that. And then in the denominator, I'm going to expand the 4 factorial because we're probably going to have to play around with that a little bit. But then the 8 factorial is down there. I'm just going to leave it as is because we're going to cancel it immediately. We're going to cancel it right now. So, gone. And then do whatever else you can do. So let's see. 4 times 3 is 12. So we can get rid of that. 2 goes into 10. I guess right now that's the only option I got left. So we're going to have 11 times 5 times 9. So that would be 55 times 9, which would be 550 minus 55, so that's 495. Okay. The next one I think you can actually do without doing the computation. And I kind of want to run through that first. So with the 7 choose 6, it's how many different ways could you pick 6 things out of 7. But if you're picking 6 things out of 7, you're leaving 1 behind. So this is effectively the same question as how many different ways could you leave 1 thing behind out of 7? And it's 7, because you could leave the first object behind, or you could leave the second behind, or the third, or the fourth, and so forth. So I think you can reason your way pretty quickly that this has to be 7. And if you do the expansion and cancel out some factorials, that is what you're going to get, because you'll have 7 factorial on top. Then on the bottom, 6 factorial and 1 factorial. Right, since 7 minus 6 is 1. And then if you say, I'm getting rid of that 6 factorial, okay, well then the top you could write as just 7 times 6 factorial. Then on the bottom, 6 factorial times 1. And yeah, you can cancel out those 6 factorials. So we can do that. And then we're just going to have 7 divided by 1, but that's 7. So yeah, it's the thing that you kind of expect. Then number 12, with 4 choose 0. Really what that's asking is how many different ways could you pick no things out of 4? Which is 1, because you just don't pick any, and that doesn't have any other arrangements. Sort of like how many ways could you pick 4 things out of 4? There's just 1 where you pick them all, and that doesn't have any other arrangements either. So you will get 1 algebraically if you expand this out, but you do have to use the fact that 0 factorial is 1. So you'd end up with 4 factorial on top, and then 0 factorial times 4 factorial. And this is 1, because the 4 factorials are going to cancel. I'm going to put this in a different color, maybe. That by definition, 0 factorial is equal to 1, not 0. That's an easy mistake to make, to think that that's 0. But if it was, this would be an undefined expression, and we know we're supposed to get 1, so it can't be an undefined expression. Number 13, this is a combination, but it's a word problem. So in an office with 10 employees, 3 are required to attend a conference. So here we just need a group of 3 people. It's not like they have specific titles at the conference or anything. We just need a group of 3. Order doesn't matter. This will be a combination. So how many different combinations are possible if we're picking 3 employees out of 10? So that is 10 choose 3. So if I expand this into the factorials, we'll have 10 factorial over 3 factorial times 7 factorial. And the usual strategy, get rid of the big factorial, is going to be in play again. So I'm going to get rid of that 7 factorial, so when I write this out, I'm just going to stop there, because I know I'm going to cancel the 7 factorial out. And I'll write out the 3 factorial, and then that 7 factorial there. So, okay, we're doing this. And then what else could we do? Let's see, the 3 has to go into 9. We don't have any options there. That's the only number on top divisible by 3. And then the 2 can go wherever, either into the 10 or into the 8. So I'm going to go into the 8, I guess. So it looks like we're going to get 120, because we're going to have 10 times 3 times 4, so that's 10 times 12. And there we go, 120. Number 14, in the denominator, one of the factorials will be a lot bigger than the other this time. 40 apartments, 2 of them will be designated as display apartments instead of being rented. So how many possible combinations of display apartments are there? So this is 40 choose 2. So that means the other factorial on the bottom should be a 38. So yeah, 38 is a lot bigger than 2. So 40 choose 2. That would be 40 factorial over 2 factorial times 38 factorial. So, yes, get rid of the 38 factorial. So on top, I'm going to write that as 40 times 39 and then times 38 factorial. Then on the bottom, I guess just a 2 and a 1 and then a 38 factorial. So those 38 factorials are gone. I don't even know we're canceling them. And then the 2 has to go into 40. So it looks like we've got 20 times 39, which would be 780. So 20 times 39, which is 780. All right. And then for a grand finale of this part, we're going to get a really big answer. So to play Powerball, really, it has another component as well. But you pick the 5 numbers between 1 and 69. Then you also have to pick the Powerball number between 1 and 26, right? So I didn't also put that in. I just have it for that first part of the ticket. We're still going to get a pretty big number here. So this is 69 choose 5. Okay, so if I expand it, 69 factorial, which is a huge number, by the way, over 5 factorial times 64 factorial. And you know we're going to get rid of the 64 factorial. So that means I'm going to write the top as 69, 68, 67, 66, 65, and then 64 factorial. No reason to write that all the way out. And then the 5 factorial will be 5, 4, 3, 2, and 1. And then the 64 factorial, which we are going to cancel right now. So that's out. And then we get into the do what you can portion of the program here. So let's see. The 5 has to go into the 65. I guess we should do that first. That's forced. Right, because 5 times 13 is 65, so we can do that. Let's see. 3 times 2 is 6, which goes into 66, so I'm going to do that just because I saw that right away. And then 4 would go into 68, and that's the only option, right? That's the only even number left on top. So 4 times 17 is 68. So what we're ending up with, let's see here. We've got, I think I got enough space over on the right for this part. 69, 17, 67, 11, and 13. And if you multiply that out, it is a big number. It's 11,238,513. Which is not the number for the odds on the back of the Powerball ticket. The number for the odds on the back of the Powerball ticket is actually this number multiplied by 26, because then you have to factor in the Powerball component of the ticket as well. But if you multiply this by 26, you get the number that's on the back of the ticket for like what your odds are to win. All right, these last couple are kind of epic. So there are combinations, but there are multiple combinations in these probability questions. So, all right, we've got a homeowner planting 6 bulbs selected at random from a box containing 5 tulip bulbs, 4 daffodil bulbs, and we want the probability that they plant 4 tulip bulbs and 2 daffodil bulbs. Okay, so they have to pick 4 tulips out of 5, and they have to pick 2 daffodils out of 4. So, okay, there's a lot to kind of organize here. So, let's just do that first, and then we'll worry about the computation. So the tulips, we'd have that there are 5 total, so N is 5, and we have to pick 4 of them, so R is 4. Then for the daffodils, there N is 4 and R is 2, because we got to pick 4 daffodil bulbs, or I'm saying this backwards, we have to pick 2 daffodil bulbs out of 4. Then all together, what's happening is that there are 9 bulbs in the box total, right? Regardless of what kind of flower they are. And we're picking 6 of them. So I think this is enough to piece this together. So the probability of 4 tulips and 2 daffodils, this is actually going to involve 3 combinations. So it's going to be, I guess, 5 choose 4 for the tulips times 4 choose 2 for the daffodils, and then all together we know there are 9 flowers and we got to pick 6. So that's what we'd have to divide by, all like the possible number of ways that you could pick 6 out of 9, regardless of if they're tulips or daffodils or how many of each you're getting. So there's a lot of simplification here, it looks like. But it might not be quite as intense as it looks. So let's see. I'll expand them all out. So we'd have, for the 5 choose 4, that's 5 factorial over 4 factorial times 1 factorial. Times 4 factorial over 2 factorial times 2 factorial for the daffodils. And then the overall, we have 9 factorial over 6 factorial times 3 factorial. Okay, well, the 5 choose 4 is really just a 5, right? And you can see it with the expanded factorials, but you can also kind of say, well, if you're picking 4 things out of 5, you're leaving 1 behind. So how many different ways could you leave 1 tulip bulb behind? 5 of them, right? Because you could either leave the first one behind or the second or the third or the fourth. That kind of thing. So, all right, if I go back over here, I probably need the entire page to write this in. So this will be 5 times, and then if you cancel one of the 2 factorials on the bottom, you'd have 4 times 3 over 2 times 1. And then in the denominator, if you canceled out the 6 factorial on the top and the bottom, you'd have 9 times 8 times 7 over 3 times 2 times 1. And then I guess we could simplify what we could simplify here and say, well, 2 goes into 4 twice, right? And then down here, 3 goes into 9 3 times, 2 goes into 8 4 times. So it doesn't look like the best 4, but I'll get a better looking 4 here in a second. So we'll have 5 times 2 times 3 on top, and on the bottom we have 3 times 4 times 7. And then we can simplify here too, because this 3 is a factor of the bottom, this 3 is a factor of the top, we can cancel them. And then 2 goes into 4 twice. So it looks like we have 5 over 2 times 7, which we do. So we've got 5 over 2 times 7, which is 5 over 14, which would be 0.3571 if you were going to write it as a decimal. There. So it looked like it was going to be a lot more intense with multiple combinations in it, but really it's maybe just a little more intense. Last but not least, we have one more example that's like the tulips. A little bit different, but similar concept, where we're going to need multiple combinations. There are two parts to this one. So we've got a part A right here, and there's a part B down below. So what do we got here? So a manufacturing company uses an acceptance scheme on production items before they're shipped. Boxes of 25 are ready for shipment, and 3 items out of the 25 are tested for defectiveness. And if any defectives are found in the 3-item sample, the entire box is sent back for screening, where then everything in the box gets screened. If no defectives are found, the box gets shipped. So what would be the probability that a box containing 4 defectives will be shipped? I think the best thing is to try to arrange everything like we did last time, like how we had tulips and daffodils. I guess here the things we're picking out of the box could either be defective or not defective. So for defective, it says there are 4 in the box, but then for the box to get shipped, we have to pick none of these, right? Because if one of them is defective, then the whole box goes back for screening. So we can't pick any of them. And so that means for not defective, we know that there are 25 total in the box, so that means there must be 21 that are not defective if 4 of them are. And then all 3 that we pick have to come from here. So then the overall total, we have 25 items and we pick 3. And so the total is pretty much what goes in the denominator. So the probability that the box is shipped with 4 defectives would be, so it's 4 choose 0 for the defective ones, then 21 choose 3 for the not defective ones, and then the total number of possible ways you could pick 3 things out of 25. Okay, so 4 choose 0, we know that's going to be 1 automatically, right? How many ways can you pick 0 things out of 4? It's 1. Just don't pick any. And then, let's see, we'd have 21, 20 times 19 over 3 times 2 times 1, because presumably with that 21 choose 3, you'd cancel out the 18 factorial. And then on the bottom, presumably, you would cancel out the 22 factorial, so you'd have 25 and 24 and 23 over 3 times 2 times 1. And then notice that really what we've got is one rational expression divided by another, and they have the same denominator. So you could cancel those. Kind of, if you think about it as dividing by a fraction is the same as multiplying by a reciprocal, then those 3 times 2 times 1s could just be canceled out. So then what we're going to end up with is 21 times 20 times 19 over 25, 24, 23. And then, as usual, we do what we can. So let's see here. 20 could go into 25, and then 21 could go into 24, because those are both divisible by 3. And then, let's see, we may not be done. So we'll have 7, 4, 19, and then on the bottom, 5, 8, and 23. We could actually go a little farther because 4 goes into 8. So we could say 4 goes into 8 twice. So this is 7 times 19 over 230. Right? The 5 times 2 times 23. That's definitely 230. So on top, that's 133. Right? Because it's 140 minus 7. So 133 over 230, which I have the decimal written down. It's 5783. So if there are 4 defectives, still a decent chance that the box gets sent out anyway. Still over 50%. Then part B. Part B is, what is the probability that a box that only has one defective will be sent back for screening? So there's one defective, we're going to have to pick it. So for this one, there, I just wanted a little more room. So defective. So one of them, and we have to pick it. And then for not defective, since we're picking 3 out of the box, we would end up with 2 that aren't defective out of 24. Since there's still 25 total, one defective, got to be 24 that aren't. So R is 2. And then the total, N is 25, and then R is 3. So we should be able to put this together. So probability of sent back with one defective will be 1 choose 1 times 24 choose 2 over 25 choose 3. Okay, so then 1 choose 1. How many ways can you pick one thing out of 1? There's only one way you can do that. So it looks like we're going to have a 1 there times, and then presumably canceling out the 22 factorials, we have 24 times 23 over 2 times 1. And then on the bottom, this will look awfully familiar because it's the same bottom as last time, 25, 24, 23 over 3 times 2 times 1. All right. And then if I just write this out as multiplication by a reciprocal, we'd have 24, 23, and then 3 times 2 times 1 in the numerator. And then in the denominator, we're going to have 25, 24, 23, and then the 2 times 1 that would be in the denominator on the top in the last expression. But then we got a bunch of stuff that we can cancel because we've got 24s and we've got 23s and we've got 2s, and it looks like we got 3 over 25 and we're basically done. And that is true. So 3 over 25, which is equal to 0.12, and that is the answer. We get a nice terminating decimal here. And that will do it for section 4.8.